A hurricane forecast doesn't predict the storm itself, it predicts the atmosphere that carries it. Think of a hurricane as a spinning passenger inside a moving flow of air. Most of its motion comes from large, slow-changing winds that stretch thousands of kilometers across the planet. If you can forecast those winds, you can forecast where the storm will go. That's why track forecasts work farther ahead than intensity forecasts. Mathematical models are physics engines for the atmosphere. They don't guess, and they don't extend past motion. They simulate how air moves, heats, cools, and transports moisture, using the same physical laws that govern wind and clouds everywhere on Earth. A computer divides the atmosphere into a three-dimensional grid. In each box, it tracks wind, pressure, temperature, and water vapor. Then it steps forward in time, seconds at a time, calculating how air flows between boxes. After millions of steps, you have a forecast days into the future. The key to a 7-day track forecast is scale. The steering patterns that guide hurricanes, like subtropical high-pressure systems and mid-latitude troughs, are huge and relatively smooth. Because they evolve slowly, the models can predict them several days ahead. The hurricane mostly follows that deep layer of winds, like a cork drifting with a broad ocean current. But the model needs a good place to start. The atmosphere isn't fully observed, especially over oceans. Satellites provide most of the data, along with weather balloons, buoys, ships, and aircraft that fly directly into storms. All of this information is incomplete and noisy. Data assimilation blends the observations with a short-range forecast to create one physically consistent picture of the atmosphere. A small improvement at the start can mean hundreds of kilometers less error days later. Once the model runs forward, uncertainty grows. The atmosphere is chaotic. Tiny errors in the initial state amplify with time. Models also simplify small-scale processes like turbulence and cloud formation because computers can't resolve everything. This doesn't make the forecast wrong, it makes it uncertain. That uncertainty is handled mathematically with ensembles. Instead of one forecast, centers run the model many times. Each run starts with slightly different initial conditions or slightly different physics, all consistent with what we know. Every run is a plausible future. Together, they form a cloud of possible tracks. When those tracks cluster tightly, confidence is high. When they spread out, confidence drops. The average of the ensemble often beats any single run. Forecasters also combine different models. Each model has its own biases. Averaging them reduces systematic errors. Human forecasters don't override the physics. They interpret the guidance, recognize known weaknesses, and weigh the most physically consistent scenarios. The ocean matters too, mostly through intensity. Warm, deep water can strengthen a storm, making it taller and allowing higher altitude winds to steer it. Coupled atmosphere-ocean models capture this feedback and can subtly improve track forecasts. So a 7-day hurricane path forecast is the end of a long chain. Global observations, data assimilation, physics-based simulations, many parallel futures, and careful synthesis. Mathematical models predict hurricane paths by predicting the evolving atmosphere that steers them, and by using probability to say not just where the storm might go, but how confident we should be.